Okay, so number 7. So we're given this stress tensor. And first it says to draw the stress element. We have positive 5.194 there. We have 1.378 in the negative z direction. Nothing on the y face. On the z face, we have to have this 1.378 for symmetry. And then we have a positive 14.806 here. Principal stresses, and I got the eigenvalues 5, 15, and 0. And then if I do the eigenvector function on that same matrix, the one corresponding to the 5 is negative 0.990, negative 0.139. This is plus or minus. And then 0.1390, negative 0.99, and then 0.10. And this is plus or minus. Well, I think, where's the question? I mean, I look at these axes and they're so similar to axes that we already had that if I look at these, I would tend to orient this with a coordinate system that's the most similar to the old one. So I would tend to say, I'm going to use the negative one of these, and that's going to be my new x. I'm going to use the negative one of these, and that's going to be my new, not next, new z, sorry. And I'm going to use the positive of this, and that's going to be my new y. And that means that they have to go in that order in the stress tensor. So my principal stress tensor would be, so that's my x, my y is 0, and my z is 15. You don't have to do it like that. You could put these in any order and use those plus or minus axes to be any axis you want. But I think it's a little easier to visualize what's going on if it stays close to your old coordinate system. Okay, so we have that. We gave the principal stress tensor. Now we want to draw the corresponding coordinate system. I mean, the corresponding coordinate system is basically, so if this is our old coordinate system, our new one is like this with just a barely, okay, so the red is my new coordinate system. So there's my new X. My new Y is my old Y. And my new Z is 0.99 in the old Z direction, and then positive negative 0.139 X. So something like this. There's the point. There's the vector. And that's my new Z-axis. I don't care at all how good you are at drawing three-dimensional coordinate axes. I really just want you to remember what these eigenvectors represent, you know. Well, you can see that these two axes are related by a rotation about the y-axis. You can see that because the y-axis stays the same. So what if you wanted to know how big that rotation was? You could go, so that rotation angle is the inverse cosine of 0.99. And so that angle is like 8.1 degrees. Now calculate the strain. I don't know if I have compliance programmed. Oh, I do. So I'll enter my compliance matrix for 110 times 10 to the 9 and then 0.25. And then I will multiply that by my principal stress tensor in Voigt form. So this is what? D? Okay, so my Voigt strain is equal to the compliance matrix times my Voigt stress. And my Voigt stress is, and we have to be careful here, the compliance matrix is almost always in pascals. So we need to represent the stress in pascals. So this is 5 times 10 to the 6, 0, 15 times 10 to the 6, 0, 0, 0. And I got 1.14 times 10 to the minus 5. Negative 4.55 times 10 to the minus 5. And positive 1.25 times 10 to the minus 4, and then 0 for all the shear. What's the maximum shear stress? So the maximum shear stress is the maximum principal stress minus the minimum principal stress divided by 2. The maximum is 15. The minimum is 0. Divide by 2 and you get 7.5 megapascals. And now to find a stress tensor that has plus or minus that maximum shear stress, we're going to do a coordinate system transformation of 45 degrees about the axis with the middle eigenvalue. So the middle one is this 5. So I'm going to do a 45-degree rotation about x.
What makes up the middle eigenvalue?
Just arrange them on a number line, max to min. 15 is the biggest one. Yeah. And so my rotation matrix is going to be 1, 0, 0, 0, cosine 45, sine 45, 0, negative sine 45, cosine 45. So my stress tensor with a maximum shear stress is equal to Q times my principal stress tensor times Q transpose. And so that is Q times, I got to enter this thing, 5, 0, 0, 0, 0, 0, 0, 0, 15 times Q transpose. And I get a stress tensor 5, 0, 0, 0, 7.5, 7.5, 0, 7.5, 7.5. And so you can see that this has at least one shear stress value that's equal to plus or minus 7.5, just like this predicted. Draw its corresponding coordinate system. Okay, so um, okay, that's asking a lot, to be honest, but let's do it. So here's our old coordinate system. Our new one is like this. And now we're going to do, and this was our X, Y, and Z. Okay, so this is our X, Y, and Z. And now we're going to do a 45-degree rotation about the x-axis. We did positive 45 degrees, so it's according to the right-hand rule. So put your thumb in the direction of the x-axis and rotate. This x-axis is going to be the same because we're rotating about that. The z-axis is going to be down like this, and the y-axis is going to be out like that. Any questions about that? So this is just, I just took the red coordinate system and rotated it 45 degrees positive about the x-axis. So like this angle would be 45 and this angle would be 45. Anybody want to see any other homework questions? All right. So now we're going back to members in pure tension compression. And last time we talked about members in uniaxial tension and compression. So that's just a tension or compression along one axis. And now we're going to talk about pressure vessels. And those are in biaxial tension. So instead of just having tension along one axis, it has it along, say, the x and y axis. Okay. And we're going to do two types of pressure vessels. So the two cases are spherical pressure vessels and so inside of here we have pressure pushing out like this. And we're really only doing these for the case where the inside pressure is higher than the outside pressure. The math looks similar briefly if you had a higher pressure on the outside, but then the mode of failure of these things would be different. Like imagine like, yeah, or like, like something that's like a undersea explorer or whatever, like those things fail in a different way. They don't just straight compress until the material fails. And then the other type is cylindrical. And so a cylindrical pressure vessel is like this. And what happens at the ends of a cylindrical pressure vessel? Well, we are not really in a position to analyze that. That gets to be more complicated. So you can imagine there are end caps on this somewhere. But to us, we're only concerned with the parts that are far from the end caps. And on this, you have pressure going around radially. And you also have pressure acting along the axis of the cylinder. For both cases, We're assuming that the walls are thin. And so what that means to us is that the thickness is much less than the radius. If you want a rule of thumb for that, let's say a factor of 10. And second, I mentioned this, the pressure that we're talking about is going to be equal to the inner pressure minus the outer pressure. And this is always going to be positive. Well, the P is always going to be positive. So we're always going to have a higher inner pressure than outer pressure. And it's not the absolute pressure on the inside of the pressure vessel that matters. It's the pressure difference between the inside and the outside. Okay. So let's talk about spherical first. And think of like a free body diagram of 1/2 of a spherical pressure vessel. And think about the loads that are acting on this. So first of all, there is, and so let me just draw a dotted line here. So we're only considering the bottom half of this thing, but this thing is in its pressurized state, and it's really an enclosed thing, right? But for us to understand what's going on, we're just going to consider the bottom half of it. So what forces are being applied to this bottom half? This is all fluid in here. And so there is pressure acting on the fluid that's in our chosen part, applied by the fluid that's excluded from our chosen part. Okay. And that is applying a total force F. And then as long as this thing is withstanding the pressure, that has to be counteracted by pulling forces applied to the metal in our chosen part by the metal on the outside, the adjacent metal of the pressure vessel that's not in our chosen body. And if this thing is in equilibrium, that also has to be F. Are you with me on that?
Well, why is, in this example, is it all going in one direction?
Good question. So the pressure you're talking about, right?
It shouldn't be like in all directions.
So remember that what pressure does is it applies a perpendicular force to any surface. Okay. And so what we have done is we have chopped this off horizontally so that the surface is horizontal.
Oh.
And that means that the pressure only acts the way we've cut it. The pressure only acts like that. Okay. There's pressure on the inside that's going towards the walls and stuff, but that's internal to our free body diagram. Oh. Okay. So the only thing external to our free body diagram supplied by the pressure is acting straight down on that surface. Right. Okay. That's a tricky key question, and that's what's going to allow us to do this calculation.
So it's only really affecting the material, everything that's kind of within beyond the material is just internal.
Yeah, beyond, like inside our free body, there's chaos going on, but remember with the free body diagram, all you're doing is trying to find the external forces. And these are all the external forces applied by that pressure.
Got it. Yeah.
And then, so now let's see what we can do to calculate that total force that's applied by the pressure. Okay, well, pressure is equal to force times area. Force is equal to pressure times area. Did I say it backwards? Force is equal to pressure times area. So this is going to be equal to the fluid pressure times the area of the fluid. And since we're assuming that these walls are thin, we're not even gonna worry about what?
The size.
Right, exactly. We're just not even gonna worry about it. I'm so conditioned now that anytime you ask a question, I assume I didn't turn on my. Okay, so pressure times the area of contact is pi r squared.
So the area is like basically just the circumference, right?
Well, the area, so first we're talking about the force of the fluid pressure. So we're talking about the area of that fluid contact. So we're talking about that inner circle area. So that's what it is. But now the key thing is that the stress that the vessel itself is under comes from counteracting that fluid pressure force. And so the force from, let's say, the metal, which has to equal this, so it's equal to P times pi r squared. Has to be, so we are going to think of this as a tensile stress times a different area. This is the fluid area. This one is the metal area. And so what's the metal area? Well, imagine this is a trick we use for thin-walled things all the time. We can approximate the area of the lip of that thing by taking that closed rectangle that makes a ring and stretching it out into a long rectangle. And so what we have is this thing that's thickness is T, and the length of it is 2 pi r. Okay, so this is equal to the stress that we're trying to calculate times 2 pi r t, little t.
What is the drawing of the rectangle representing?
Okay, so that's representing that we're calculating the area of this ring.
Oh, I see. It's just unraveled
By just opening it up. And
the circumference of the sphere times the thickness of the metal.
Right, that's right. And it doesn't work generally for a ring that you unwrap like that, but as the thickness goes to 0 in that limit, they're equal to each other. Okay, so now all we have to do is set these two things equal. And so we have P times pi r squared is equal to 2 pi RT times the stress we're trying to calculate. The pi's cancel. One of these r's cancels. And you get that the stress is equal to PR over 2T. So this is a normal stress that's parallel to the, or I should say tangent to the surface of the sphere. Because of the symmetry of the sphere, this is a normal stress for any tangent, like along any tangent axis to the sphere. So this is the normal stress for any tangent axis. So let me draw that. So if this is our sphere, and we want to know what the stress is at this point on the surface, we can set up a coordinate system with x and y tangent to the sphere and z pointing out. So x and y are tangent.
Is this dot inside or outside?
Outside. It's on the, well, it's somewhere in the middle. But remember that this is thin, so there's no difference in the behavior anywhere inside the metal. Okay. And so the final result is the stress tensor, computer. If you're using a coordinate system with your z-axis pointing out of the surface like this, your stress tensor is for x, PR over 2t, for y, PR over 2t, and for z, 0, 0, 0. So that's the state of stress for any point in the material.
For a sphere.
For a sphere, yeah. So notice, and for thin walls. But notice your coordinate system always needs x and y tangent to the sphere. And z, normal. Is this a principal stress tensor? Yes, because there's no shear stresses, which means that so the if you wanted to calculate the maximum shear stress, it would just be half of this, right? Just according to the maximum shear stress formula. So okay, let's do a calculation example. So let's say we have a spherical pressure vessel. And the radius is 0.1 meters. And the thickness is 1 millimeter. The outer pressure is atmospheric pressure. So 1.01 times 10 to the 5th pascals. And the inner pressure is 5 times that, 5.05 times 10 to the 5th pascals. And we want to calculate the maximum shear stress in this container. For this vessel. So we can just go straight to this formula. The maximum stress is P times R over 2 times T. P is 5.05 times 10 to the 5th minus the outer pressure, 1.01 times 10 to the 5th. So 4.04 times 10 to the 5th pascals. Okay. And so we can plug this in. We have 4.04 times 10 to the 5th times a radius of 0.1 divided by 2 times the thickness. And you get a value of 2.02 times 10 to the 7 pascals. If you wanted to write the stress tensor, then it would be 2.02 times 10 to the 7, 2.02 times 10 to the 7, and so the maximum shear stress is 2.02 times 10 to the 7 minus the minimum, which is 0, divided by 2, so 1.01 times 10 to the 7 pascals.
When you rotated it, would be like a four of the matrix spots would be all shear, right? So like it was in the last example where we did the maximum shear stress. It was biaxial.
I think only 2. But looking at this coordinate system, you would want to rotate your coordinate system 45 degrees about the middle eigenvalue axis. So that would be either 45 degrees about x or 45 degrees about y if you wanted to find a stress tensor with a maximum shear value.
The other example was the two loads were 5 and 15, and then rotated around. Yeah, 5, but it won't work the same way. Rotated it. This sensor both the same.
Any questions about that example? Yep.
How do you know you did that good calculation right?
How do I know we did it right?
Yes. Is there any way to check?
I don't really know of a way to check that except just coming back later and doing the calculation again, you know. and seeing if it matched. Any other questions? Okay, so now sort of similar thought process for cylindrical pressure vessels. And the part that we are going to consider is far away from the ends. So you can just think about this part. We're not worrying about what's happening at the ends. And there are two types of stresses that we're going to consider. In the sphere, everything, there's so much symmetry. Every kind of stress is the same. The stress in every direction is, well, in every tangent direction is the same. But with a cylinder, you can consider a stress that's the two halves of this sandwich holding themselves together, right? That's called the hoop stress. Can you picture what I'm talking about here? So like if the material failed in this way, the top of that sandwich would just blow straight up into the air, you know? And then there's another way that this thing can fail, and that is stress like this. Okay? If it failed in that way, the left half of the sandwich would blow away from the right half. Well, I'm going to Subway for lunch. Okay? Any
You said the first one, the horizontal, was called the hoops stress.
Hoop, like, because it's like the integrity of a hoop, like it's trying to blow a ring apart, kind of.
Okay.
Yeah.
And is there a name for the one that's vertical or like?
Yes, that is called. Do I have that written down? What is that called? I'll have to tell you later, but there is a name for it. Okay, so the first. So first, we're going to consider the. So the black slice. So these are the stresses that would blow the top off this sandwich. I like this sandwich thing.
It also makes sense.
So to do that, we're going to take basically the same approach we took with the cylinder. We have a rectangle like this. And then we have walls. These are thin walls again. I didn't draw them very thin, but. And then okay. So this is our free body diagram, our free body. And I'm going to use the same colors as before, green for the pressure, red for the. So thinking about it the same way that we thought about the spherical pressure vessel, what's the direction of the pressure force that the top, like omitted material, is applying to the material that's included in our body? So our free body is the bottom of the sandwich. The top is still there, it's just not included in our free body. So think about the material, this fluid inside, and think about the fluid for the top part. What's the direction of the force that fluid pressure from the top is applying to the fluid on the bottom? Straight down, yep. That's right. And so we have a force here that's like this. And if that was the only force that was being applied, this thing would blow in half. But the material provides the counteracting force, and that's going to be a normal tensile force like this. Okay, and so we have an F from the material, we have an F from the fluid. Those have to be equal if this is in static equilibrium. So let's think about first the force from the fluid pressure. That force is equal to the pressure times the area. And so the area of that that exposed area of fluid that's just a rectangle. So we just want to calculate the area of that rectangle. It's 2 times the radius is the, think of it as like the height of that rectangle, times the length. And then that's the area, and then we're multiplying it by the fluid pressure. So we have 2RLP. And now we're going to calculate the force applied to the metal by the metal above. And so this is going to be the stress times the area of the metal. And the area of the metal is just, so think of this as two long rectangles. And those are equal to, so 2 times the thickness times the length. Now for static equilibrium, we'll set these two equal. There are L's on both sides that cancel, 2's on both sides that cancel. And we get that the stress in the material is equal to PR over T. Okay, so that is twice as big as the spherical stress. And now we're going to go to the red seam. So the red slice. And so now we're going to calculate stresses that would blow the left and right halves of the sandwich apart. And so to think about that, our free body is going to be like this, and the material we're emitting is over here. Okay, so you have a pressure force like this, and a metal force like this. And those have to be equal to each other. One of those is F, the other one has to be F. So the force from the fluid pressure is the pressure times the area. And the area is just the area of that inner circle, where again, we're not worried about the difference between the inner circle and the outer circle area because we're talking about thin walls. So this is just pi r squared. And now the force from the metal, or applied to the metal, is the normal stress times the area. And again, that area we can get by imagining unhooking this ring and stretching it out to make it a rectangle. So this is the thickness times the circumference, and then we still have that stress. And so we'll set these two equal to each other. We have P, or pi times P r squared equal to 2t pi r sigma. We'll cancel one of these r's and the pi, and we get that sigma is equal to p r over 2t. So notice what we're going to see is that for the cylindrical pressure vessels, the X and Y normal stresses are not the same. And so you have to think a little bit more about the directions in this case. So sigma XX is not equal to sigma YY. So if you have something like this, and you're trying to calculate the stress at this point, we would have a z-axis pointing out. I'll call the x-axis along the length and the y-axis there. And so the principal stress tensor in this case is equal to PR over 2T for X. PR over T for Y. And 0, 0, 0. Okay, so let's do an example here.
It's similar, same as that's.
Yes, one of them is the same as spherical, and one of them is twice as big. So let's say we have a pressurized cylinder with a radius of 0.5 meters and a thickness of 0.005, so 5 millimeters, and a pressure difference of 1 times 10 to the 6. So that's the inside minus the outside pressure. What's the maximum shear stress in this container? So the first thing you should ask yourself is it reasonable to consider this a thin-walled?
Because it's 10 less.
Yeah. So if the cutoff ratio that we're going to use is a factor of 10, this is a factor of 100. So that's fine. And our stress tensor is so pressure times the radius, so 1 times 10 to the 6 times 0.5 divided by 0.01. And then this one is 1 times 10 to the 6 times 0.5 divided by 0.005. And so we get 5 times 10 to the 7. And then 1 times 10 to the 8. When stresses get up into the times 10 to the 8, that's probably pretty bad news for how things are going to go. Yeah. I mean, just for metals in general, for steel or anything, like if you ever see a stress up close to 1 times 10 to the 8, it's unlikely that it's going to withstand that, I think. Okay, so, but we're trying to calculate the maximum shear stress. So that is equal to the maximum minus the minimum divided by 2. So 5 times 10 to the 7 pascals.
You know how much pressure like a balloon, like a latex balloon holds, or like a tire does?
Do I know?
Like in pascals?
In pascals. Okay, yeah.
It'd be much lower than steel, right?
Yeah. Yeah, let's do a conversion right now. Like what's a tire? 40 PSI, something like that. It's a lot bigger than 40. I know that. 40 PSI 2 pascals. 1, 2, 3, 4, 5. So about 2.8 times 10 to the 5 pascals is like a tire, what a tire can withstand, normal tire pressure in a car. Which is, so remember that standard atmospheric pressure is just over, barely over 1 times 10 to the 5. So that's about, so a tire can hold like 3 times, well, I guess 4 times, you put 4 times atmospheric pressure inside, 1 time outside, and the difference is 3 times atmospheric pressure. Yep.
Questions. The first one, for the exams, do you need to remember how to derive?
No, I will just give those to you as formulas.
Yeah.
And I'm not going to give you a ton of problems related to this either. Yeah.
The second question is, when I can choose to divide by 2, there's 2 equations now.
Yeah.
Which one?
Well, you have to think about the 2 directions. So, so line your X and Y axes up tangent to whatever point you're looking at, with the X axis along the length of the cylinder. And then this is the stress tensor. Okay.
I have a question. But how is principal stress is going to look on the exams when, like, you won't have our computers to, like, calculate the...
Yeah, I mean, I guess I can't remember what I've done on past exams with that, but I'll either just give you principal stress values, or I'll give it in a way that it's really easy to calculate by hand, where you just have to use the quadratic formula or something. I can't remember. I'll tell you more later. I'll look at old exams, and I don't remember how I do that. Any other questions right now? Okay, so this is it for pure tension and compression for members. So we've done trusses, and now we've done pressure vessels. And now we're going on to a bigger topic that's going to take up a lot of this class, which is stresses in beams. So for stresses in beams, we're going to start out with a review and a little extension of internal loads. But we'll go all the way through internal loads again, so you'll get a refresher on that, or if you haven't seen that before, you haven't seen it much, it'll be fine. And then we'll use the internal loads to calculate the stresses at different points in the beam. Okay, goodbye.